Hello, everybody. Welcome to another puzzle time with MoMath and MathPickle. So today we are going to be building a twisted home. And here is an example of a twisted home. What does a twisted home mean? It means that every single one of the rooms, we can take that room and we can rotate it. And it has mirror symmetry. It has rotational symmetry. So for example, this green region here, if I was to take it and I was to twist it on its head, it would look exactly the same. It's got rotational symmetry. So all of your rooms have to have rotational symmetry. This is an example of a home where every single room has rotational symmetry. So that's a good thing. But that's not the only rule. The second rule is that all of the rooms must be different. Here, you can see that the red and the green room are exactly
the same.
So it doesn't work. The orange and blue rooms are exactly the same. So this doesn't work. The third rule. I've already said the third rule. Everything must have rotational symmetry. So this is not good because the red region, it has mirror symmetry, but it doesn't have rotational symmetry. And the purple room has no symmetry at all. So that doesn't work. The last rule, I'm going to get you guys to guess. Go ahead, Ruta. Do you want to guess what the last rule is? Why does this not work? So the first rule works. All of them are the same size. Okay, all of them have exactly 4 parts to them. The second rule works. They're all different. Those regions are all totally different. The third rule works. They all have rotational symmetry. So what do you think the fourth rule is?
I'm not really sure yet.
Okay. So the fourth rule is that all of the rooms must be connected. So here, this orange room, it's not really a single room. It kind of looks like a double room. Okay? So all of the rooms have to be connected. The blue room also, it doesn't look like it's just one big room. It looks like it might be 2 rooms glued together at a corner. So that also doesn't work. So those are the 4 rules. Again, first rule is they have to all be the same size. You can't have a small room and a big room. Second, all of the rooms, no 2 of the rooms can be identical. So this doesn't work because of that. Third rule, all of the rooms must have rotational symmetry. And last rule, all of the rooms have to be connected. So you can't have a room like this orange room or this blue room, which are not really connected.
What's the rules? I wasn't here for the beginning.
Yeah, so there's 4 of them, and you'll catch up as you go here. So, Oscar, do you want to make the first 4 size 4 room?
A, B, E, F.
A, B, E, F. And what color?
Purple.
Purple it is. Okay. Seth, do you want to make a second room?
Sure. DHLP.
GHLP?
No, DHLP.
DHLP, right.
Because to have a line go down, you would have to put it on either C to O or D to P. And because C to O would isolate D to P, we'd have to go from D to P.
Okay.
Is this even possible anymore?
These could be impossible. I reserve the right to fool you at any time of my choosing with a problem that is impossible. Okay. Go ahead, Tin Can. do you, oh my goodness, this is now looking hard. Is there any room that you can fit in there that has rotational symmetry that's not like one of the other rooms and is the same size? So it has to be size 4. Go ahead, Tin Can, if you can find any room in there that might work. Leanna Bodiford.
Oh, hello.
Hi there. Is there
I
another room?
missed the intro.
That's
are
fine.
we
So
guessing?
what we're trying to do is we're trying to fill this with same sized rooms. This is a home. You're trying to fill it with same sized rooms, all of which have rotational symmetry and all of which have to be connected. So it might not be possible, but try to find is there another room that's different from the others? It can't be the same shape.
Oh, it can't be the same.
It can't be
Okay.
the same shape, yeah. So
Ooh,
here we have this purple one that has, I'll just pop in this.
I see
Here.
there's a purple one and a red one. Okay. Rotational symmetry.
And this has symmetry too.
No, I see 2 that are the same, but I don't.
Maybe we're at our limit. Maybe we find all of the possible ones.
I mean, can they be connected diagonally or only on the sides?
Yeah, so they have to be connected, and diagonal connections don't work. So for example, here, in this example, the orange doesn't work because it's not connected. And the blue one also doesn't work because it's only connected at a corner. So that's why this one fails.
Yes. Okay, I see.
Yeah.
I don't see one.
Yeah. It's Oscar, do you want to do you think that we've got them all of the possible rooms here? Or?
Well, I'm still sticking with the purple, but maybe we can try to do something with but maybe we can remove the HLP and try to do something without a long line.
Okay. So you in this configuration, without removing anything, you've given up, Oscar.
I'm saying that maybe it'll work if we remove the long red line.
You're giving up on it in its current form. You're saying, I don't think there's any more rooms that we can fit in here.
I know this. We can do CGKJ, but then and the last room would be the same shape.
And does that have rotational symmetry or mirror symmetry?
And that doesn't have rotational symmetry.
Yeah, it doesn't have rotational symmetry. So we're totally messed up. This is not looking good.
I have an idea, a possible idea that, wait, can it have only 1 dot or can it have 2 dots?
Remember why this one failed?
Oh.
This one failed because they weren't all the same size. So you have to have them the same size as well.
Okay.
What do the dots do?
The dots, I'm just showing you where the rotational symmetry occurs. So you can take that dot, you can rotate A, B, E, F around, and you will end up with the same shape if you rotate it 90 degrees or 180 degrees. You'll end up with the same shape if you rotate it around that dot.
So
Same with
it's
this.
impossible to do a 1 by 1.
It's impossible to do a 1 by 1.
Mm-hmm.
Yeah, because it's the wrong size. So like this here.
Then all of them have to be 1 by 1s.
So, oh yeah, that would be a possibility,
That
except
would work.
the second rule is that they all have to be different shapes.
Yeah, I know. That's why I said it wouldn't.
Yeah.
I think so.
So are we finished? This doesn't work for 4 by 4.
Oh, I think I know how to solve it.
Seth, you've got another, or Taco Cat?
I don't know if Seth knows it too, but if we go I to O,
CIO?
No, I to O.
I to O. Okay, and
I
which
don't
other
think
ones?
that has
E to G.
rotational.
Oh, like this.
Then what
Sure.
about
Okay,
the
so
X?
that
If
certainly
we color
has
in I, J, K, M, N, O and make a 2x3.
IJKNO.
Yeah,
Um,
I, J, K, M, N, O. I guess that's another possibility if we make an M in 1x1 and then C, G, K.
Okay,
But then we
so
can also have C, G.
okay, so this certainly has mirror symmetry here. Sorry, rotational symmetry and mirror symmetry. And this one here, we can make this one, what color? Let's make it that
Green.
color. So
Although if we didn't color the M and K in and made C, G, K and then the M make a 1x1, that's another way to solve it.
sure.
They all
Okay,
have
so
to be the same
solving it like this only breaks one rule, and that is that they're all the same size. Otherwise, you guys have solved it. Okay. If you go like this, then this one here, that's the right size. So we can't solve this here. These are the right, that's the right size. And we've managed to fit in 3 rooms.
Why can't we just?
Oh wait, how is the other impossible? I don't.
Why can't we just make this whole thing one color?
Sure, you could do that, and that would be a pretty unsatisfying house to live in. There'd be no kitchen, no bathroom, no bedroom. It's just one big room. So if you want to live in a house like that, be my guest. But most people choose to differentiate rooms. That's what these twisted people want to live in.
But why was
happens
the
if we
one?
make every-
They were all different sizes.
Okay, so many people talking at the same time. So Taco Cat, you're first.
Why didn't the first solution work? They were all the same, different shapes, and sizes.
Okay, so this was the, let me just grab that. Okay, so this is the solution that you're talking about here. Can people say why this solution doesn't work?
I think I know.
Go ahead, avocado cream.
They're all different sizes. They're all supposed to be the same size.
That's right. So according to our rules, the first rule was all of the rooms have to be the same size. So that's why this fails. And this fails because we can't find a 4th shape.
Okay, can I say my thing?
Oh, I didn't get it. So it's impossible, I guess.
Can I
So this might be impossible.
say
Absolutely.
my
Go ahead,
Can I
avocado cream, your turn.
I was gonna say about the thing where it's like there just have to be one big room. I'm like, that's all my Minecraft houses in a nutshell that I make in survival.
Okay, so
True,
we're
it's
gonna,
just one floor, one room, a roof.
so we're gonna
Yep.
call this avocado cream's ideal home, and we're just gonna put one rotationally symmetric circle in the center. And
Let's call it Avocado Cream's Minecraft house.
yes,
Yep.
that's avocado cream's Minecraft house. Good. So we've got that sorted out. Whew. Next, so we suspect that this is impossible. I also suspect that this is impossible. In fact, yeah, I'm really quite certain that this is impossible to solve. And
Time for a poll.
oh, a poll. Thank you very much.
Oh,
Oh, that
yeah.
was perfect timing.
Dun, dun.
yeah, perfect.
Okay.
I don't know why it's still showing that I'm saying something, even though I was like not saying anything. It's like take off your.
Trying to work here, guys. That's fine. Okay, here we go. So let's see. Yeah, I'm pretty sure that this is impossible with all of those rules in place. So whenever that happens, we try, maybe it'll be easier going for a 5 by 5. Maybe it'll be harder and we'll end up with an impossible problem again. Maybe this will be possible. Any ideas about how to go about this? Solly, do you want to start?
We could do avocados cream Minecraft house.
How would we do that? There's not really a middle.
Oh, sure, there's a middle. I could do the middle right in M, in the middle of M, right there.
Okay.
There you go. Yeah, there you go.
That's
There
one
you
way to
go.
do it. But this is a 25. So let's try and make it into 5.
Okay.
So I think if we did something like what symmetrical stuff is there?
So that's a really interesting point. So Solly, your idea is, instead of just jumping right in here, what symmetric possibilities are there for, and you wanted to do a 5, so those are called pentominoes. You wanted to do pentominoes. So I'll tell you right now, here's one pentomino that works. Can you name any others? So there's one that works for sure. And Solly, yeah, you've named another one that works. So there's 2 that work. So I'll put it up here, Solly.
But that's trapping the C.
Okay, I'm just kind of counting now what are the different ones. I wasn't actually trying to solve it. So let me actually go, and to answer your question, I'm just going to go onto this blank piece and I'm going to make it much, much smaller. Actually, I know what I'm going to do. Instead, I'm going to go to this ridiculous one here, and I'm going to find all of the 5. So we're not solving this. We're not solving this. Instead, what we're doing is we're answering your question, Solly. What shapes are of size 5 that have mirror symmetry? So there's one. Taco Cat is suggesting just this 5 here. And you want to do that green. There you go. And Solly, you were suggesting this one here. And we can do that blue. There we go. Oh, Taco Cat is suggesting this one here. Okay. Yeah, so try to find all of the pentominoes that have rotational symmetry. So this is a different way to try to approach the problem. Rather than just jumping into the 5 by 5 grid, you're seeing, oh, I wonder, is this, have I got enough pentominoes? I need 5 of them that have rotational symmetry. So Seth is suggesting this one. Are we going to say that this is the same or different from the pentomino, from this pentomino? So now we've got this kind of an S and the kind of a, yeah. So Taco Cat is suggesting this one here.
That one's not going to work.
Why not?
Well, it doesn't have rotational symmetry. You need to rotate it all the way around. And I'd also say the 2 blue ones are the same. They're just left.
Right. So these 2 blue ones, Oscar is saying that they're the same.
I don't think they're the same. They're not exactly the same.
Get why the purple one doesn't work, because if you notice the green one right next to it, you can also flip it in such a way that it's in a different position.
Okay, right. So the purple one, yeah, it doesn't have rotational symmetry. So this one here, it has mirror symmetry, but it doesn't have rotational. So let's get rid of that. The disagreement between Oscar and Seth about whether these are the same or different that is not something that you can argue. That's just a matter of definition. Either you are defining these two as being different, or you're defining them as being the same. Either you can flip your polyomino, your pentomino over, in which case these would be the same, or you can only slide them, in which case you can't rotate one to be the other. So this is not something that you can argue. You shouldn't argue about this. You should just say, okay, what's a reasonable choice for this puzzle? So let me just get this green right here, and let's get this red one right. So will we find any others, or is this it? We've only got these 4.
Wait, someone said something about the green
We need to
W.
get one more to solve the puzzle.
Oh yeah, the green W here.
Doesn't work.
Doesn't have rotational symmetry around here.
When you turn it 180 degrees,
So I have another one that would work.
2 squares will be on the other side.
Yeah, this doesn't have rotational symmetry. It has mirror symmetry. It has mirror symmetry along this axis. It does not have rotational symmetry, so we can get rid of that. We've already got the straight one, so that one we don't have to count again. So we can rotate this object here. We're going to say that it's the same as this one here, because we can certainly rotate one of those into the other
So I
one.
think we've proved that this is impossible.
If those are the only ones, then this would be impossible. Yeah. I
What do
agree.
you name this puzzle?
Is there
This puzzle is called Twisted Homes, and I will just show you for 4. These are all of the polyominoes with exactly 4 squares.
So
Okay,
this is
these are
possible.
called tetrominoes.
Wait, no, this is not possible.
And this is not possible either, because you can see there are only 4 tetrominoes. There's only 3 tetrominoes that have rotational symmetry. So of course it's impossible to fill it. Taco Cat, you can't use the last 2 that you added there do not have rotational symmetry. So you can't use them in this puzzle. The only ones that you can use in this puzzle are this one, and this one, and that's not enough to fill it. So we've proven now that this is impossible. There's no way, even if you spend years doing it, there's no way.
Mm-hmm. Absolutely.
I am going to release you guys onto trying to solve this. We've proven that the 4x4 is impossible. We've proven the 5x5 is impossible. And now it's time to experiment with other ones. I'm going to share this presentation. Okay, and I'm going to put that in the chat. Okay.
One time in one of the Zoom docs, someone was called an anonymous neon cat, which is apparently really rare. So that's nice.
Okay, so if you want to stay with me, we will be working on the 6x6 on this slide. You will not be able to edit this presentation. Instead, all that you need to do in order to grab your own version of the presentation is go up here to File, choose Make a Copy and Entire Presentation, and then you'll have your whole own presentation to play with. And then at the end, in 15 minutes, you can copy your favorite slides. Then I'll open up this presentation. You can copy your favorite slides into this, and we can talk about them.
Now, something that I have to say is that you have to be logged into a Gmail or a Google account to actually file and make a copy.
Sure. So if it doesn't work for you, just stay with me and be happy, people.
I'm just gonna stay with you anyways.
Okay, that's good. That's good. Okay, So we're going to try to solve the 6 by 6 and go ahead. Anyone who is going to try to work on this, you can try to solve 7 by 7, 8 by 8.
I don't see it.
Link isn't in chat.
Yeah, the link is in chat.
No, link isn't.
No, the
Oh,
link
it's not
is
in the
not.
chat.
Oh, someone direct messaged me. That's why. Okay, let's try that again. There we go.
There we
Now
go.
everyone has it.
I'm probably gonna open it in case if I want to do it later. Okay, but I'm gonna stay with you.
Okay, good. Right. So how would you like to progress? Ruta or Angie, if you want to jump in, and you can progress like we did the first time, which is we just try to start filling in. Here we've got some choices. We, instead of choosing a, okay, so of course we always have the choice of doing the Minecraft house of one giant room.
I have a
courtesy
question.
Of avocado cream. But if we
I have
choose
a
not to
question
do
about
that,
how it works on Google Slides. How do you select multiple squares?
on Google Slides, you
You
just
press,
click.
so you click on the square and then you press shift and then you click on other squares. So you gotta press shift to select multiple squares here.
I believe this puzzle is impossible.
For the 6 by 6 as well, Solly.
Oh, I haven't checked the 6 by 6. Let me see. I can't find this 6 by 6. That's probably why.
Okay.
Okay, 6 by 6. No, that's 5 by 5. That's
So there's two different ways to go. We can either start adding these polyominoes of whatever size you choose into this 6 by 6, or we can choose Solly's approach, which is to find all of the polyominoes of whatever size you choose and see how many we can find. And maybe it'll be impossible. So those are the two approaches. So Ruta or Angie or Kestrel or Tin Can, jump in and yeah, tell me what, even if you don't want to solve it, you can just tell me, oh, let's try to solve it in this way with 6 or with 12. Yeah, I don't know what's possible here and what's not. I guess we could also choose 18. But don't forget that everything has to be different. So this here was illegal because not everything was different. So I think if you choose 18, two 18s, it's going to be difficult to make them different. Whenever you guys are thinking, I'm just going to label these.
You can't do the 6 by 6 because there's only 4 of the shapes that would work, I think.
Only 4 shapes. Are you choosing size 6 for your shapes?
Yeah, I'm choosing size 6.
I found
Oh yeah,
7.
it doesn't work with size 6. It doesn't work with size 6.
Yeah,
Okay.
I think
Because there's only 4
six-
shapes that would work for this situation. There's more hexameters than just 4, but I'm saying there's only 4 that would work.
Only
I found
4 with
7 shapes
With
for this
6 though, so 6 by 6 is still possible. I
6
think,
by 6.
possibly.
I don't understand how it can be possible if you've just shown that there's only 4 shapes of size.
For 6 squares for the 6 by 6, but the 6 by 6 might be possible with other.
Got it. Okay. So let's, again, let's go and I'm just going to go I and JJ. Okay. Okay, and let's make I'm going to make these all bigger so that you guys can see them all. So can someone confirm that there's only 4 shapes that have rotational symmetry that are size 6?
I found 7,
7. So 7 would be enough. That
but
would
I
be
can't
enough to
find
tile.
a solution that fits all of them.
Okay, make this nice and big, and then I'm going to go like this, and I'm going to center it. Boom. Okay, there we go. Yeah, 7 would be enough. And in fact, let me see. I have got 7. So here are the 7 that I found that have rotational symmetry. Now, this certainly looks difficult to pack all of those into that square. I'm not saying this looks easy. I'm just muting you, Sully, because there's a bumpy kind of noise there. But I think that this is what I find as well, that there were these 7, but that doesn't mean that I have any idea how to solve this. Does this look, how many people think that this looks impossible? Thumbs down. How many people think that this is probably possible? Thumbs up. We've got Oscar with the thumbs down, Solly with the thumbs down, avocado cream with the thumb going right across the screen. Ruta with a thumbs down, Taco Cat with a thumbs down. Yeah, even though we've got enough of these.
Well, are you going to use Taco Cat? Are you going to count Avocado Cream's Minecraft house as a solution?
Why
Minecraft.
not?
No. That's not a real home. A real home needs at least 2 rooms, I think. I think we should.
Minecraft wooden house.
I've got a question about
Go
the
ahead,
6 by
avocado cream.
6.
Sorry, go ahead, Oscar.
I was saying, since 8 and 9 are factors of 36, and maybe it's possible if you use both sizes of pieces.
Yeah, I absolutely think we should try 9. I think 9 is possible. You might be able to do it. Do you have ideas?
I don't have ideas.
Okay. But I share your, if not optimism, at least not abject defeat. I think there's a possibility that we might be able to pull something off. For the 9, for the showing for 6s, it was easy to find all of the 6s that have mirror symmetry, that have rotational symmetry. It was easy to write them all down, and there were 7 of them. For the 9s, to be able to write down all of the 9s that have rotational symmetry and then try to fit them in here, that doesn't sound fun.
I saw you had a page with all of the 7s, and there's already a lot of 7 ones.
Yeah, a lot. So yeah, it looks like we need to adopt a different strategy depending on which ones we're trying to fit in here to be efficient. In this case, with the 9s, with your 9 idea, Oscar, I don't want to go and find all of the 9s that have rotational symmetry. I want to just try to fit them in. But maybe there's not that many. I don't know. Oh, you know something interesting? With 9, in order to have rotational symmetry, because can you ever have a situation like this where whatever shape that you're finding, that your shape has got something like this? Can you ever have this?
No, I don't think you could have a dot in the corner.
You can't have a dot in the corner because if you have a dot here with rotational symmetry, it means that there must be an even number. There must be an even number of squares, right? So we know right away that this is impossible to have the dot right in the middle. So that's not going to work. And I think for the same reason, we can't have a dot in the middle between two shapes.
The only 9 that I can think of that has rotational symmetry is a 3x3 square.
Okay, is that the only one? Or
Well,
is
there
that
has
just-
to be more, but
1
it's
by
the
9.
only
1 by
No.
9.
a 1 by 9? It's not going to fit, but yeah, 1 by 9.
1 by 9's not going to fit.
Okay, let me just get this here. What? Why doesn't this work? Okay, arrange, ungroup. Aha, I have it all grouped. Got it. Okay, here we go. So here is Oscar's discovery of the 3x3. Is this a solution? This L shape, this big L shape?
It wouldn't work.
No, it doesn't have rotational symmetry at all. It has mirror symmetry, but not rotational symmetry, right? You can bend that around this axis here.
Yeah, that
around
L
the KJ.
won't
You can
work.
bend it like a butterfly or an airplane.
I'm just brainstorming.
Yeah, so that's not going to work. I'm just wondering, is there any? Okay. Number one, I think that we have figured out that whatever solutions we have here, this circle has to be on a single square. Otherwise, we're going to end up with an even number of squares. So that's for sure. But
I
now
think the
what?
smaller the board, the more possibilities that it's possible. But then if it's a super big board, then there's probably, I mean, with really big boards like 100 by 100, there's just not a number big enough with enough rotational symmetries.
Oh, so you think that there won't be 10 blocks that have rotational symmetry? There won't be 10 polyominoes that would help fill a 10 by 10 board. So you're guessing that this is always impossible, no matter what size.
Yes.
Is that right?
Twisted houses, those words. You're just gonna have to stick with the regular house. Sorry, twisted people. You're gonna have to come into normal houses.
So here are two that have look okay, but there's actually a lot, right? Because you can take this and you can color, okay, and do.
Without rotational symmetry, I think almost anything would be possible.
Yeah, but with rotational symmetry, you think everything is impossible?
I mean, I tried doing the 8 by 8 with polyominoes that consist of 8 squares, and I tried that with the 6 by 6, the 5 by 5, and the 4 by 4, and they all came out impossible. So until it's disproven that.
Can we find 312? Because
312s?
yeah, this consisted. You can make 312s.
It's like the
Yeah,
difference
we
Well,
could try 312s. So
For a first 12, you could do a 2 by 6 or a 3 by 4.
I
sure.
wonder.
Okay, so let me do both of those.
I wonder if our house is in a square in some abstract shape.
Yeah, I
Although
bet
you
then it
can't
would
do
also be-
both because then and I don't think you'd be left with a shape that works in most cases.
If there wasn't, I think if you could remove one rule, everything would be possible.
Yeah, it seems like we've made too many rules for this. And maybe it's impossible, totally impossible for all sizes. Okay. Avocado cream, that was a fun background music that you had there, but I muted you. So the 12 solution, like it looks so close. It's not going to work, but it looks so close. So what do you guys think? How many solutions have I found to this puzzle? I'll show you the best that I've done. So this is the proof that the 4x4 doesn't work. You can prove that the 6x6 doesn't work either for sixes. And then I tried the 8x8, and I can't prove that this is impossible. But if I took a vote right now, I would put my thumbs down. I don't think this is possible.
You can and delete the one that looks like a hole because that'll just make the middle trapped.
Yeah, good, Oscar. Absolutely right. I've got an extra one here which I really can't use. Exactly right. So
even if we weren't talking, even if one of the rules were we don't need rotational symmetry, we couldn't use that.
Yeah, true, because we have that other rule that says that everything has to be connected.
It violates 2 out of 3 rules.
Yeah, that's a great way to think about it. Yeah. Okay, so here we have a problem. Is that we have a problem, and I have yet to find a single solution to it. So I told you that I was going to give you impossible problems. I don't know if this is impossible. I actually suspect that this is possible for larger grids. Just the number, you can see here, it was impossible, and you can figure that easily. There's just not enough. Here, there's enough, but they're just difficult to fit together. Here, my suspicion is that this is impossible, but I can't prove it anymore, and it's not obviously impossible. The corners, I think, are where the problem happens. Yeah, go ahead, Taco Cat.
There's probably some really advanced mathematical formula that in hundreds of years some Galileo 2.0 will have, because NIM, like, it has like all these weird.
Well, the idea that this is going to be solved with a mathematical formula, I think, is not right. I think these are most of the puzzles that I present are sufficiently difficult to formulate into something that could be solved like that. So I don't expect that this is going to have a pretty solution, Taco Cat.
Yeah, but there will probably be like a written down proof or disproof.
I think if there is a proof, it's going to be, here is a solution. Here I have solved the 10 by 10 or the 12 by 12. I'm guessing that it's going to be an even one that gets solved first. That's just my guess. I will also guess that if the answer is that there is actually no solution for any of these, I'm guessing that no one will be able to prove that. I guess
then it's guilty until proven otherwise.
It could be extremely hard to prove that it's impossible to solve. But my guess is that this is possible. If I had to wager, I would guess that this is probably possible by 10 by 10 or 12 by 12. But I'm not going to be the person who solves it.
I know a way to disprove it. You can just write down all the possible ways of formulating it. But it's probably easier to prove it than disprove it.
Yeah. The problem is that that becomes exponentially difficult. So I don't use a computer. I could solve this by hand, and I could prove that this is impossible by hand. If I was to do this by hand, and I suspect I could do so, this might take me a day to go through all of the options. I would start at a corner. Which ones can fit in a corner? Okay, so these ones can fit in a corner, these ones can't. So let me separate those out. I need 4 that fit in a corner. Okay. Of course, I've got this one that fits in 2 corners, but that would create 2 other corners. So I think it's safe for me to say that this might take me a day to say that this is impossible. Why are you crossing off this one, Taco Cat? I understand this one. I don't understand this one. They
don't go into corners, because if you put that one in a corner,
okay. So now you're getting rid of corners. Okay, fair enough. Yeah, that's right. These don't go into corners. So yeah, that could be. I think that would be the most useful way that I would tackle this, and it might take me a day to solve this by hand. By the time I get to 10 by 10, I can imagine that it might take me 2 weeks to solve anything. And so by the time we get to 12 by 12 or 14 by 14, it's my lifetime, and I've got better things to do with my life.
Taco.
Wait, these 2 here can still go in the corner.
Yeah.
This one can go in the corner.
I don't
can't go in the corner when you flip.
That one, how would it go into a corner?
Good.
It won't go into a corner in a square.
Okay, I'll show you. Okay, so let me go and put this one here into a corner. So this is 8 by 8. Okay, so I'm going to put this one into the corner. Okay, so if you can erase the your things, then it's like this. Something like this. Is that right? Oh, that's not quite big enough. I need one more. Okay, leave it like this. Okay, there we go. So there's one that's in the corner. Now you can see it does create problems. Like, for example, here, this is impossible to fill. So I totally agree with you. This one can't go in a corner, but it's not a trivial, you can't trivially say that it doesn't go in a corner. You have to argue a little bit more to say, well, if that goes in a corner, it creates a problem. And this one here, this is now impossible.
What about the other one then?
Yeah, maybe there's a whole bunch that you can rule out. So this is the way that I would tackle the problem, is I would look at the corners and I would try to show that there's not enough. There's not enough that fit in the corners without making another problem. So, okay, so there is a disappointing puzzle time with MathPickle and MoMath. We have worked really hard and we have got exactly zippo, nada, nothing. We have not been successful at all for any size, and we are left with dismal failures in our wake.
That was sweet.
Well, the only way that like any of them could work would be going with the avocado cream's Minecraft house idea, but twisted people don't like that.
Yeah, but you're maybe we could find, like, for a 12 by 12, maybe we could find a solution that that doesn't just take 12. Like, part of this problem is maybe that we're just trying to solve an n by n square with n rooms of size n. Oh, that's complicated. Let's.
What if we make one without making it a square and make it like, I don't know.
Shape.
Yeah, but I can say that this puzzle time was fun. I think it's fair to say that.
Mm-hmm.
Is what?
Fun, I think. Right, Taco?
Yeah, it was definitely fun.
Okay, good.
We had some Einstein vibes today.
Good. Yeah, but that's quite typical of being of working in the real world with tough problems. Is some days you arrive and you leave and You have done nothing successfully. This
Okay.
is an example of one of those days.
Wait.
Well, I'm
I'm going to quote somebody here. We did not.
Well, you
we
proved
were
that
not
nothing
wrong.
was
We were not
impossible.
wrong, but we learned many ways not to do it.
Yeah, yeah. Okay, take care, everybody.